Welcome back. So please watch our previous video where I explained the block sphere representation of different single qubit states. All the different possible single qubit states are on the surface of the block sphere. Different states occupy different points on the block sphere surface. Because there are infinite number of points on the sphere, there are infinite number of possible states for a single qubit in general. But when the qubit is measured, the wave function collapses and the possible outcomes are 0 or 1. Now let us move on to the matrix representation of qubits. The qubit states form a linear vector space. These qubits can be given a matrix representation. The computational basis ket0 and ket1 have the following representation. So the ket0 is written as a column matrix 1 0, and ket1 is another column matrix 0 1. A single qubit state psi is equal to a ket0 plus b ket1 in the matrix representation becomes ket psi is equal to a 0 has the representation 1 0 plus b multiplied by the matrix representation for ket1 is 0 1. So when you multiply these scalars into the matrix and add them, it is just a column matrix with numbers with elements a and b. So a column matrix with element a b, where a and b are the probability amplitudes, is the matrix representation for a single qubit state. So the conjugate of psi, ket psi, is the Bragg psi. It is written in this fashion: Bragg psi is equal to, so the transpose of a column is a row matrix. So you make it a row and replace a and b, they are complex numbers, you remember, with their corresponding complex conjugates. A star and b star denote the complex conjugates of a and b. So what do I mean by a complex conjugate? If I have a complex number z is equal to x plus iy, then its complex conjugate is just replacing the sign of the imaginary part. X plus iy becomes minus x of x minus iy. Change the sign of the imaginary part, you get the complex conjugate of a complex number. So Bragg psi is obtained from ket psi by transpose conjugate. The transpose of a matrix is obtained by interchanging rows and columns of the matrix. That is what had been done. And the conjugate of a matrix means replacing all the elements of the matrix by their corresponding complex conjugates. When one does both transposition and conjugation of a matrix, it is referred to as transpose conjugate. So to go from ket psi to Bragg psi, you do a transpose conjugate. Interchange the row and the column and replace the elements by its corresponding complex conjugate. So we can verify the normalization condition on a single qubit state in the matrix representation. So you know what is Bragg psi? It is a row matrix a star b, b star multiplied by a column a b. So you know how to multiply matrices. A star a plus b star b. Complex conjugate a multiplied by the number itself is norm squared for the complex number. So you have mod a square plus mod b square, or more precisely it should be called the norm squared of the complex number. This has to be equal to 1, which is the normalization condition. So the matrix representation of the following qubit states are given below. So if you have 1 by root 2 ket 0 plus ket 1, so you know a and b. Now what are the values? A is equal to 1 by root 2, b is also 1 by root 2. So just substitute them in the matrix representation. You have all the different matrix representation for the different possible single qubit states. So in the first example, example A, I have A is equal to 1 by root 2, B is equal to 1 by root 2. So the matrix representation is a column matrix with elements 1 by root 2, 1 by root 2. In example B, the elements are A is equal to 1 by root 2, B is equal to minus 1 by root 2. So the matrix representation becomes column matrix, first element 1 by root 2, second element minus 1 by root 2. In example C, the coefficients A and B are 1 by root 2 and I by root 2. So you use them in the representation. So the matrix representation would be 1 by root 2 and I by root 2 column matrix. And finally in example D, the elements are A is equal to 1 by root 2 and B is equal to minus I by root 2. So using that in the matrix representation, so the matrix representation would be a column matrix with elements 1 by root 2 and minus I by root 2. So homework: for all the above qubit states, calculate the normalization condition Bragg-Psi and verify whether they are normalized. To find out the Bragg-Psi, all you have to do is do the transpose conjugate of it and then do the matrix multiplication. It has to be equal to 1.